The Feynman Lectures on Physics. This lecture, Conservation of Energy, was presented by Dr. Richard Feynman on October 6, 1961, at the California Institute of Technology.
There will be no summary of the previous lecture. There's no summary of the previous lecture, just to remember whatever you can remember from it. No vital points. The next two lectures after today will be given by Professor Matt Sands because I'm going to a meeting in Brussels. And I'll come back next Tuesday, the Tuesday following. Today's lecture is on one of the laws of physics and beginning, of course, the detail looking at the different aspects of physics. We've just finished our description of things in general, and now we look at more specifically, in particular, what a law of physics looks like. And so I picked one out to illustrate the ideas and the kind of reasoning that might be used in, say, theoretical physics. So the lecture today is on the conservation of energy. There is a fact, or if you want to call it a law, governing all natural phenomena that's known to date. There's no exception known to this. It's exact as far as we know. And the law is called the conservation of energy. It states there is a certain quantity, which we call energy, that doesn't change in the manifold changes which nature undergoes. Now that's a very abstract idea because it's a mathematical principle. It says that there's a numerical quantity that doesn't change when something happens. It's not a description of a mechanism or anything. It's just a strange fact that you can calculate some number, and when you're all finished watching nature go through her tricks, you calculate the number again, and it's the same. Something like the bishop is on the red square now, and after a number of moves, details unknown, it's still on some red square. It's a law of this nature. Since it's an abstract idea, I would like to illustrate the meaning of it with a rather peculiar, silly example, but it does illustrate the idea. I want you to imagine a child, perhaps Dennis the Menace, who has blocks. But you must appreciate that these blocks are absolutely indestructible and cannot be divided in pieces. They're just, each is the same as the others. And we'll suppose that he has, say, 28 blocks. Now this child is put into a room by his mother in the beginning of the day with his 28 blocks. And at the end of the day, I don't know why she's so curious, but she counts the blocks very carefully and discovers a phenomenal law that no matter what he does with the blocks, there are always 28 blocks. So this goes on for a number of days until one day there are 27 blocks. But a little looking around shows that there's some under the rug. You have to be careful to make sure that you look everywhere in order to make sure that the number of blocks doesn't change. One day, however, the number of blocks appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and now looking outside, you can find the other 2 blocks. So you bring them back in again, and everything's all right. Another day, careful count indicates the existence of 30 blocks. This causes a considerable consternation until it's realized that Bruce came to visit, and he owns blocks. And left, perhaps, a few. So after we've gotten rid of some of these things, that we close the window, we don't let Bruce in, then we see everything's going along all right until one time when we count there are 25 blocks. But there's a box in the room, the toy box that the boy has, and the mother goes to open the toy box, but the boy says, "No, don't open my toy box," and screams. He doesn't want them. The mother is not allowed to open the toy box. Being, however, extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces, say. So the next time when she wants to check, she weighs the box again, subtract 16 ounces, and divide by 3. So she discovers the following number of blocks that you can see that you have to add to this number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces, and then it's constant every time, up to a point. There then becomes some gradual deviations. There appear some deviations, but careful study indicates that that dirty water that's in the bathtub is changing its level. In other words, the child is throwing blocks into the water. You can't see it because it's so dirty. But you can find out how many blocks are in the water by adding another term to this formula, which is height of water in tub minus 6 inches divided by 1/4 of an inch, because each block that goes in is 1/4 of an inch. And so with a gradual increase in the complexity of the world, you find a whole series of terms representing ways of calculating how many blocks are in places where you're not allowed to look. And as a result of this, it's possible to find a complex formula, a quantity, which has to be computed, which always stays the same in this situation. Now, I will now describe the analog of this to the conservation of energy. The most remarkable aspect of it is that I want you to abstract from this picture, first, there are no blocks. You never see the blocks. So you take away that term. Then you discover yourself calculating more or less abstract things. The analog has the following points in it. First, sometimes when you're figuring out the energy, some of it leaves the system and goes away, or sometimes some comes in. So in order to verify the conservation of energy, you've got to be careful that you haven't put any in or taken any out. Second, that energy has a large number of different forms, and that there's a formula for every one of the different forms. I've written a number of the forms here. I see I left out elastic energy. And there's a formula for every one of these things. If we find out what the formulas are and then total them up, it won't change except for going in and out. I'll give you that. Well, we can do that down if you want. So that's the relation of the analogy. It is important to realize that in physics today, we do not have any knowledge of what energy is. My analogy is bad because we do not have a picture in physics today that energy comes in little blobs of a definite amount. It does not that way. And it is not definite blocks, but there are formulas for calculating some numerical quantity. When you add it all together, it gives 28. Always the same. We have no deeper understanding of it than this. And it is an abstract thing and doesn't tell you the mechanism or the reasons for the various formulas. Now, the conservation of energy can only be understood if we have the formula for all these things. And I could, of course, list the various formulas for different forms of energy. We call these things different forms of energy, different hidden ways of calculating the number of blocks. However, I want to amuse us today by discussing the formula for gravitational energy around on the surface of the Earth here, not going very far away. And I wanted to derive this formula in a way that has nothing to do with history. It's simply a set of reasoning which I have invented for this particular lecture. And it's patterned after a very excellent argument by Mr. Carnot on the efficiency of steam engines, but it's applied here to calculate or to understand the law of how to calculate the energy and what the conservation of energy is in the case of gravitational energy. So what I want you to do is to consider weightlifting machines. That is a machine which has this property that you put a weight here, it lifts another weight while lowering some other. I want also to make an hypothesis, which is that there's no such a thing as perpetual motion with these weightlifting machines. In fact, that there's no perpetual motion at all is a general statement of the conservation of energy law. I must be careful to define perpetual motion. First, let's apply it to weightlifting machines. If you've lifted and lowered a lot of weights, take the weights off, you can restore them and restore the machine to the original condition. And find when you're all finished that the net result is to have lifted a weight. Then you have a perpetual motion machine because you can use that lifted weight to run something else, provided that the machine which lifted the weight is brought back to exactly the same condition as it was before. And furthermore, that it's completely self-contained, that it hasn't received the energy to lift that weight from some external, but Bruce's blocks haven't been thrown in. Now, I have a very simple weightlifting machine here. Here's a machine for lifting weights 3 units strong, which I put on this panel. By placing a weight on this panel, In order to get the thing to work right, however, I'll explain about this. You have to lift this little thing. Now, we just don't worry about that, but that lifts this. That lifts this. On the other hand, I could lift the 1 unit weight by lowering the 3 unit weight, provided I cheat a little bit by lifting the one on this side. I want you to realize in any actual lifting machine, I have to add a little extra to get it to run. Please disregard that temporarily. The ideal machines won't require that. They don't exist, and we'll come back and discuss that little business, that in order to make it work, I have to move this. The machine that I have here is, in the sense, almost reversible. That is, if it'll lift the weight of 3 by lowering a weight of 1, then it will also lift the weight of 1 the same amount by lowering the 3 the same amount. Nearly. So we imagine that there are 2 classes of machines, those which are not reversible. This is really not reversible because I have to fiddle around with these little extra weights. But we have a machine, so a general machine is not reversible. In fact, any real machine is not precisely reversible. But as we improve the fulcrum and the levers and so on, we find that the amount of stuff that has to be lifted gets weaker and weaker. And so, with our imagination, we idealize to the possible existence of a reversible weightlifting machine. So suppose that there were such a thing. Suppose now that I have a reversible machine which does this. A 1 unit weight, let's say a pound or any other marker for the unit. 1 unit weight is lowered by 1 foot, say, or any other unit of distance, doesn't make any difference. And when this happens, the machine lifts a weight 3 units, say, as this one does. And that's all the machines I'm going to consider now, all the various devices. This is the simplest possible one. I get screws and axles, inclined planes, and all kinds of levers and machinery can be inside. But the net result of the machine that I want to discuss is that it takes a 1 pound weight, lowers it 1 foot, and in doing so, lifts a 3 pound weight some distance. Now let's suppose that we have machine A and this reversible machine. And this particular reversible machine lifts the 3 pounds a distance x. And now I have another machine, a machine B, which is not necessarily reversible, is not reversible, or is, whichever you want, is or is not important. Let's say it isn't for the sake of argument. It lifts 3, a distance y. Now what I'm going to prove is that y is not higher than x. That it is impossible to build a machine that will lift a weight any higher than will be lifted by a reversible machine. Let's see why. Well, let's suppose that y were higher than x. I don't have to draw pictures. I can wave my arms. Look. You take a weight, 1, and you lower it 1 foot with the machine B, and that lifts the weight 3 up a distance y. Now you lower that. See, if y is greater, I'm going to prove, or let's say what I'm going to prove. Y is not higher than x. Suppose it were. Then I've lifted the weight higher than I need. Then x, the distance, say y is up here. And suppose x is only this high. Then I can lower the weight from y to x, obtaining free energy, free power. And then use the reversible machine A running backwards, which according to this will lower a 3 pound weight, x, and lift the 1 pound weight 1 foot, which will put the 1 pound weight back where it was before. And I'm ready to use machine B again. In other words, I lift with machine B by lowering the weight 1 pound. I lift the thing 3 pounds up y. Then I lower it a distance x and get my 1 pound weight back before. But since x is less than y, I have a little bit left to go. I can make the thing do something on its fall between y and x. And therefore I have perpetual motion. So if y were higher than x, I would have perpetual motion, which I assumed was impossible. So therefore, with those assumptions, I deduced that y is not higher than x. Therefore, of all the machines that can be designed, the reversible machine is the best. No matter how you figure out with the wheels and the gears, you'd better try to make it reversible. Now I'll show you something else. All reversible machines must lift at exactly the same height. Because suppose that B were really reversible also. Well, the argument, if B is reversible, that y is not higher than x is, of course, just as good as it was before. So y is not higher than x. B is now reversible, however. And I could make my argument the other way around. You stop and think a minute, you see what I mean. I could make the machines run in the opposite order. So I could just interchange the B and A in the argument. And I can easily prove the other thing, that x is not higher than y. In other words, if I had two reversible machines and one lifted higher than the other, then I can use that extra difference and then make one run the other backwards to keep the cycle going. So therefore, if I have a reversible machine, all reversible machines lift the same distance, no matter how they're constructed. If they drop 1 pound, 1 foot, and lift 3 pounds, the same distance, no matter how they're constructed. This then is a very remarkable observation because it permits us to analyze the heights at which different machines are going to lift something without looking at the interior mechanism. And we know right away that if somebody has concocted a series of levers that's enormously elaborate, that lifts this a certain distance, and I compare it to a simple lever like this, which is a fundamentally reversible, I know this is going to lift it no less high. I know exactly how high it's going to lift, and I know that it's no use trying to redesign the machine to get greater height. So you see that this X is a very important general proposition for all machines. To summarize, every reversible machine, no matter what, or no matter how it operates, which drops 1 pound by 1 foot and lifts a 3-pound weight, always lifts it the same distance x, irrespective of the machine, and therefore something in great generality. It's a universal law of great utility. The next question is, of course, what's x? After all, it's an interesting law to discover, because it's the same for all machines and doesn't depend on any particular one, so I can get the x that way. One way is to invent a reversible machine and figure out how high it lifts. But I have a more ingenious argument for you that tells us what x is, and so I'd entertain you by the following argument. Suppose that we have a reversible machine which is going to lift this distance x, 3 for 1. I set up a set of 3 balls here. This is only a rack to hold the balls and it doesn't move. This ball is being held on a stay up here at a distance 1 foot above the ground. The machine lifts, if I put, this is the other part, this is the machine here. There's this platform and this piece here. And the machine is of this nature that if this goes down 1 foot, it can lift 3 balls, lowering 1, by a distance x. Now I arrange that the platform which holds the 3 balls has 3 shelves, or 2 shelves on the floor, 3 shelves, exactly spaced at distance x. And I further arrange that my rack which holds the balls over here are all spaced at distance x. I measured the distance x and I found out what it is, and so I laid this thing out and I'm all ready for the argument. Now when I roll the balls from here to here, and I suppose that takes no energy because I don't change the height. So I load the balls onto the platforms, and I get into this condition. Now, the machine operates in the way it's supposed to operate. This reversible machine operates. It lowers this ball to the floor, and it lifts this rack a distance x. Now you see how cleverly, ingeniously arranged is this rack here. These are spaced at a distance x, and so these balls are right even with the platforms that they can be rolled out onto, and so I unload the balls here. Now, having unloaded the balls, I can restore the machine to the original condition without the ball. That's the property of the machine, that it can be, that after you've lifted the weights, you can restore the machine to this original condition without any extra energy. So now I have 3 balls on the upper 3 shelves and 1 down here, naturally, having lifted essentially these 3 balls up. But you see, the funny thing about it is that in a certain way of speaking, I haven't lifted these two at all, in a way of speaking. Because after all, there were balls on that shelf before. There are still balls on those shelves. So in a net resulting effect of the whole thing really has been to lift the ball from here to here. One ball, you see, net result. In order to illustrate better, suppose that we rearrange the balls by moving this one over here and this one over here. Then you'll see better what I mean. Now I roll this ball into this hole and roll this ball across over to this position. Then you'll see that these three balls are just exactly the same as they were in the initial condition, but that the fourth ball here is at some other height, which is 3x. If this 3x exceeds 1 foot, then I can lower the ball from here to here running some other machine and getting power free, and then I'm back in the initial condition and can run my apparatus again. Therefore, 3x cannot exceed 1 foot. For 3x exceeds 1 foot, I can make perpetual motion. Now likewise, you can prove that 1 foot cannot exceed 3x. I leave it to you to work it out. All you have to do is to start around the other way, make the whole machine run the opposite way. It's a reversible machine, and the same argument can be carried the other way in which you lower things. In other words, if the 3x were lower when you started out than the 1 foot, then you can show by running the same argument in the opposite direction that you would make perpetual motion. Therefore, 3x is neither greater nor less than a foot, and we discover then, by argument alone, the law that the x is 1/3 of a foot. I'm sure the generality is clear to you that if 1 pound falls a distance, a reversible machine can lift 3 pounds to 1/3 the distance. Or, if 1 pound falls a certain distance in operating a reversible machine, then the machine can lift p pounds a piece of the distance, 7 pounds a seventh of the distance, and so forth. And that now gives us the law of, we can state the law of the conservation of energy this way. Then, another way to put the same thing is the following. That 3 pounds times the height lifted, which in our problem here was x, is equal to 1 pound times the height, the distance lowered, which is 1 foot in this case, or 12 inches, or whatever you want to. Excuse me. Yeah. So, another way of saying this is the following. If I take all the weights and multiply them by the heights that they are now above the floor, all weights in the problem, multiply all the weights by the heights above the floor, and then let the machine operate, and then multiply all the weights by all the heights again, there'll be no change. That is the sum of this for all the weights. This symbol means add. Weights times heights for all the different weights, added together, is unchanged. We'd have to generalize this single case where we moved only one weight to the case where when we lower one, we lift several different ones. But you can use the same kind of arguing to deduce this too in a more general case by having more elaborate machines. I just illustrate the type of reasoning, but this is deducible from this type of reasoning. That is, if we take the machine, for instance, that starts with one up here at a foot high and 3 on the floor, and then after the machine is operated, the 1 is on the floor and the 3 is up in the air by the distance x, then the way of calculating this way is the following. In the beginning, it's 1 pound by 1 foot. That's for the first weight, plus 3 pounds times 0 feet. How convenient, it's easy to calculate it. And that turns out to be the same as 1 pound times 0 feet plus 3 pounds times x feet. Of course, it checks every time. That's why I'm telling you about it. It's the same thing. This, we call this term, the sum of the weights times the heights, gravitational energy. The energy which an object has because of its relationship in space relative to the Earth. And the formula for gravitational energy, as long as you're not too far from the Earth, the force weakens as you go higher. So this is only approximate. You might try to find out where the error is in this analysis if the heights are so high that the force weakens. Gravitational energy has the formula, the sum for all the various particles. We don't have to remember the sum. It's always a sum of all the things that are there. You add it together. Weight times height. And that's an illustration of it. Now, the question is, of course, it's a very beautiful set of reasoning. The only thing is, maybe it's not true. After all, nature doesn't have to go along with the reasoning. Perhaps, for instance, perpetual motion is in fact possible. So that some of the assumptions may be wrong, or I may have made a mistake in reasoning. So it's always necessary to check. And it turns out experimentally, in fact, to be true. Incidentally, the general name of energy, which has to do with location relative to something else, is called potential energy. In this particular case, more specifically, I would call this gravitational potential energy, to give you a high-class word. If it's a question of electrical forces against which you're working, instead of gravitational forces, you're lifting charges away from some other charge with a lot of levers, then the energy content is called electrical potential energy. The general principle is that the change in the energy is the force times the distance that it's moved, that your force is pushed, and that's a change in energy in general. But we come back to a lot of these things and make them when we go on with the course, of course. Now this principle, the conservation of energy, is very useful for figuring out what will happen in a number of circumstances. And I'll illustrate some of those. Just because you probably learned an awful lot of laws in high school to figure out what happens under different circumstances, I assure you they're all the same thing. So you didn't have to memorize 75 rules. You could figure it all out. Take the simplest example as an inclined plane. Suppose that we have an inclined plane which is happily on a 3, 4, 5 triangle. And we have here a weight, which we'll say a 1 pound weight on the inclined plane with a pulley here. And on the other side of the pulley is another weight, X or W, say unknown. We want to know how heavy this has to be to just balance that. Now, how can we figure that out? Well, we say, if it's just balanced, then it's reversible to move up and down. And I can consider the following situation. In the initial circumstance, I suppose that the weight, the 1 pound weight is down here, and that the weight W, say, is at the top, wherever it is, that is, and there's a pulley here, so. And then after, when it's slid down in a reversible way, now, we can do it back and forth because it's balanced, then we have here the 1 pound weight at the top of the thing, and the weight W is down here, some distance or other, from the place it was before. What distance? The slant distance, 5 feet, or 5, whatever they are, 5. So the weight W has fallen 5 while the weight 1 is lifted 5. No. It's the height above the ground, the formula says. How far did we lift the weight? We only lifted the weight 3 feet. So therefore, we lifted 1 pound by 3 feet, and we lowered W pounds by 5 feet, and therefore W is 3/5 of a pound. So you see, you can deduce that by very cleverly from the conservation of energy. Cleverness, however, is relative. It can be deduced in a way that's even more brilliant from the conservation of energy by a way invented by Stevinus, and which is on his gravestone, his tombstone. That's his tombstone. And that explains that it has to be 3/5 of a pound. Because it doesn't go around, says he. And it's evident that this part of the chain is balanced. So the pull on these 5 weights here must balance the pull on the 3 weights here. So whatever the ratios of these legs are, and it's even true if it's a double incline. And so you see, by looking here, that it's 3/5 of a pound. So this was clever, but that's even more clever. It's 1600. Anyway, if you get an epitaph like that on your gravestone, you're doing fine. Let me illustrate with the more complicated problems that the same thing works, and you don't have to. This is very simple, but let's take one of those wonderful things that they're always annoying you with. Something like this, you see. We'll just make one of these up. I have one made up. I have a screw thread, so a jack, you see, which has a screw thread on it like that, that's in a nut, and that you turn it with a long lever in the nut, in the jack here, and the lever is 20 inches long, say, and you push it around this way, and that there are 10 threads to the inch on the jack. That's an inclined plane, you see, of some kind of complex inclined plane. And I'd like to know how much force do I need here to lift 1 ton here. A ton is 2,000 pounds, say. So let's see. Suppose that I want to lift the ton 1 inch. Then I have to turn this around 10 times. So to lift 2,000 pounds by 1 inch, I have to turn this 10 times around. When it goes around once, it goes 2 pi times 20. It goes around a distance of approximately 125 inches around per turn. So I must really turn 125 inches is the distance that I go. And if I had various pulleys and so on, I would be lifting an unknown force, unknown weight, W, to balance. And so you find out what W is. It's about 1 pound and 0.6, according to this. Well, it came out 2 pounds last time. Oh, I see. I had 8 threads per inch. That made it easier. But anyway, with 10 threads per inch, it comes out 1.6 pounds for the push. And you see it's by the conservation of energy. To take still another example, we'll take a somewhat more complicated one. Consider the complex problems of this dopey nature, which is that you have a rod, so a bar, which is supported at one end, and it's 8 feet long. And then in the middle of the thing, at 4 feet, somebody has put a weight of 60 pounds. Or, I don't know, it's a bridge and there's a truck on it, huh? And there's another truck, it always makes it sound better when they say that. There's another truck of 100 pounds. No, there's no truck of 100 pounds. There's a Morris Mini Miner here at a distance of 2 feet from the fulcrum. We would like to know how hard do we have to pull over here in order to keep all this stuff from falling down, disregarding the weight of the rod. So we say, okay, we'll sort it this way. Suppose you had a pulley here and you had a weight down here hanging on the pulley. How big would the weight W have to be in order that this thing all balance? How can I figure that out? Well, I imagine that the weight falls any old distance. I picked, to make it easy for myself, I suppose that the weight went down a short distance, 4 inches. That is, I imagine that this lever would lift itself up around this fulcrum, like the dotted line here, a height here of 4 inches. How high would then the 60-pound weight lift? Well, it's easy to see because it's 4 stay young. So it lifts 2 inches here, and this one is a quarter of the way, so this lifts 1 inch here. Therefore, the principle that the sum of the heights times the weights doesn't change, the change in this will be 0. In other words, the weight times 4 inches down, if you like to think that way, you can put the equation any way you want, plus 60 pounds times 2 inches up, plus, that's up, 100 pounds times 1 inch has to add up to nothing. You don't, if you do it with minus signs, otherwise you put ins and outs are equal. It's the same thing, of course. And so you have here 120, 220 divided by 4 is 55. You know, it looks good how fast he does arithmetic, but he's done it before and he checked the number, so I know it's good. So you find you have to have a 55-pound weight there to balance it, and thus you can work out the laws of balance, statics, of complicated bridge arrangements, and so on. This is called the principle of virtual work, because in order to do this argument, we had to imagine, virtually in our imagination, that it would move a little bit. Even though it's not moving, we use the motion, and we use a very small motion, because if I try to use 400 feet here, it would get a little bit confused by having gone around so many times. So we use a very tiny motion, so it's easy to figure out. The smaller, the more easy it is to figure out. Actually, you see, it goes in a curve, and it isn't exactly 2 inches and so on. But you take an infinitesimal distance, and that's called the principle of virtual work, which is uses the principle of conservation of energy to get the laws of those systems of this kind. Now, that's not the only kind of energy, and in order to illustrate a more, another type of energy, we take another form of energy. You consider a pendulum in which when you drop it down, you let go and it comes back. It lifts itself up. It lowers, and where did the energy go? I took gravitational energy. When it's down at the bottom, it hasn't got it anymore. It's lost. But nevertheless, it can climb up again. And the way it climbs up is because the way we must keep track of it is to say, although it's lost some gravitational energy here, it has another form. Evidently, of course, it's in motion. And it's by virtue of its motion that it's able to climb up the height again. So we have the conversion of gravitational energy into some other form when it comes to the bottom. We have to get a formula for the energy of motion. I would like to illustrate, as well as I can, that the weight by gravity, even if it does interchange into motion and come back into gravity, cannot in any way increase the height in which the ball is left. In other words, this ball can't possibly come any higher than the point at which it was left. So we have the situation that when the thing has fallen to this distance, it's lost its gravitational energy, and if the law of conservation of energy is right, there must be in some other form, and that form is motion. So we would expect, if the law of conservation of energy is right, that it doesn't make any difference what kind of a way it comes up. And you see, if you can, that even if it comes on a shorter arc, it comes to the same height as if it's left. That is, the motion is converted into the height by the pendulum, and it doesn't make any difference by what machine the motion is converted into the height, provided it's reversible. And a pendulum is nearly reversible. There's so little friction up here. So that this will go to the same height. If we had it at a different place here, of course, it's a little different, but it comes to the same height here. And the situation is here, what's it going to do if it can't quite make it? So there we are. Now when we see that when at the bottom of the swing it has less gravitational energy, it can still recover. And the energy that it has at the bottom of the swing depends on only the height that it came down, only the height that it has to recover. We illustrated by the pendulum that it doesn't make any difference by what route it recovers the height. It is able to come up to the same height. Therefore, in the motion at the bottom is a quantity of energy which permits it to rise a certain height and has nothing to do with the machinery by which it comes up or the path by which it comes up. So that we have an equivalence formula, something like that one that we wrote for the child's blocks. We have another form to represent the energy. And it's easy to say what it is. The kinetic energy at the bottom is given by the following formula. The kinetic energy at the bottom is the weight times the height that it could go corresponding to that velocity. Well, we just said that. But what we need is the formula that tells you, given this, we want the formula in terms of the velocity. See, to every velocity that corresponds a certain height by some rule or other that has to do with the motions of objects. If we start something out with a certain velocity, say straight up, it'll reach a certain height. We don't know what that is yet, but it depends on the velocity. There's a formula for that. Then the formula for kinetic energy must be, if you see an object moving with velocity v, calculate the height that it could come to, and multiply by the weight. That'll be correct. Now, when we learn about the laws of falling bodies, you probably know that the formula for this, the relation between the velocity and the height, is in fact that the height that it can go is the square of the velocity divided by twice a constant, which is called a gravitational constant. So with that formula for the height in terms of the velocity, we can write this thing this way, that the kinetic energy is the weight times the velocity squared over twice the gravitational constant. And so for different speed objects, we can calculate the kinetic energy, the energy of motion. And the energy of motion is nothing but the weight times the height that that motion could lift it to if it was shot straight up. Of course, it hasn't got to do with the fact that you're in a gravitational field that motion has energy. It doesn't make any difference where you got the motion from. That formula for kinetic energy is more general than the particular place, a general formula for various velocities. Both of these formulas are approximate. This because it's not right when the heights are wrong, when the heights are so high that the gravity is weakening. This because of the relativistic corrections of high speeds. But when you get the exact formula for the energy, then the law of conservation is exact. Well, we could continue this way and illustrate the existence of energy in other forms. One that's not written there is elastic energy. If I pull on this spring, I have to do some work. I could use lift weights with it. Now that I have it down, I can lift weights with it, right? So therefore, in its expanded condition, it has a possibility of doing some work. So if I just added the sums of weights times heights, it wouldn't check out. I have to add something else to account for the fact that the spring is under tension. It's in some way. I must add a term, which I should add in here, elastic energy, which is a formula for in a spring when it's stretched. How much energy is it? And so here, for instance, if I let go, then the elastic energy is converted as it passes through the middle to kinetic energy and goes back and forth into compressing the spring and elastic energy, and it's reversible back and forth between elastic and vertical motion. But and this goes on, so that there's an exchange there between elastic energy and kinetic energy. There's also some gravitational energy going in and out, but you can do this experiment sideways if you want to. Incidentally, now it's gotten into a peculiar condition. It's not moving up and down. It's in the same position as it was before. Where's the energy that I put in? Now the energy is in rotation when it's turning. But when it's turned all the way, where is it? It's in twisted spring. So we have converted energy from vertical pull of a spring to vertical motion to rotational motion to rotational twist of a spring, and so on back and forth. It keeps going until the losses destroy it. Now come the losses. I cheated all the way through. I'm pulling little weights. I'm telling you the thing goes on forever, but in front of your eyes you see that it's stopping. Where's the energy when it's all finished moving up and down? In other words, I have the sums of the weights and everything else. What happened? What happens in all these circumstances is this, that inside the springs, the things are made out of lots of atoms. And although with great care in the delicacy of the arrangement of the parts, you can make things so that as you roll something on something else, none of the atoms do any jiggling at all. You have to be very careful. Ordinarily when you roll, because of the irregularities of the material, there's bumping and jiggling and the atoms start to wiggle inside. So we lose track of that energy. We find the atoms are wiggling inside here now. After this is slowed down, they're jiggling in there in a random and confused manner. There's still kinetic energy, all right. There's kinetic energy, but it's not of the object. What a dream, huh? How do you know there's any kinetic energy? It turns out that with thermometers and so forth, you can find out that in fact it's warmer, and that there really is a development of kinetic energy by a definite amount. And this form of energy we call heat energy, but we already know that this is not a new form. This is just kinetic energy, of internal motion. And one of the troubles with all these experiments that we do with matter on a large scale is that we can't really demonstrate the conservation of energy. We can't really make our reversible machines, because every time we move a large clump of stuff, the atoms do not remain absolutely undisturbed, and so a certain amount of random motion goes into the atomic system inside. And we can't see that, but we could measure that with thermometers and so forth in the form of heat energy. There are lots of other forms of energy, and of course I can't describe them any more in detail. There's electrical energy that has to do with pulling and pushing by electric charges. There's radiant energy, the energy of light, which we know is a form of electrical energy because light can be represented as wigglings of the electromagnetic field. So this thing is equivalent to this. This one is equivalent to this. There's chemical energy, the energy which you call the energy which is released in a chemical reaction. Actually, elastic energy is to a certain extent something like chemical energy, because chemical energy is the energy of attraction of the atoms one for the other. And so is the elastic energy. So both the elastic energy and the chemical energy are forces of the atom. Why do I cross them out? Because our modern understanding of these is the following, that this chemical energy has two parts. Kinetic energy of the electrons inside the atom, so part of it is kinetic, and electrical energy of interaction of the electrons and the protons, and the rest of it, therefore, is electrical. So with electrical and kinetic, we have an understanding of these other forms. Next, we come to nuclear energy, the energy which is involved in the arrangement of the particles inside the nucleus, and we have formulas for that, but we do not have the fundamental laws. We know that it's not electrical, and it's not gravitational, and it's not purely kinetic. So we don't know what it is, so there's an additional form of energy here. Finally, associated with the relativity theory, there is a modification of the laws of kinetic energy, or however you want to call it, so that this is combined with another thing called mass energy. It turns out that an object has energy from its sheer existence. If I have a positron and an electron that are standing still, that are doing nothing, never mind gravity, never mind anything, they come together and disappear, energy, radiant energy, will be liberated in a definite amount. And the amount can be calculated from only knowing the mass of the object. It doesn't depend on what it is. We make these two things disappear and we get a certain amount of energy. When a mass is m, mass is weight divided by g, by the way, so if you like, this is mass times velocity squared over 2. This is the way to remember it. It's much better because it has nothing to do with the gravity that way. Then the formula here is mass times the speed of light squared is the energy associated with the mass. Now there's a couple of things to say about the laws of conservation of energy. In the first place, I think it's obvious from my explanations that a law of conservation is enormously useful in making analysis, as we illustrate in a few examples without knowing all those formulas. But if you had all the formulas for everything else, you can figure out an awful lot of things, lots of things should work without looking at the details. Therefore, conservation laws are very, very interesting. The question is, what other conservation laws are there in physics? There are two other conservation laws which are exactly the same as analogous to the conservation of energy. One is called the conservation of momentum, and the other is called the conservation of angular momentum, and we'll find out more about those later. Deeply, we do not understand the conservation of energy. I mean, in the last analysis, we do not understand the conservation of energy. We do not understand energy as a certain number of little blobs. You may have heard that photons come out in blobs, and that the energy of a photon is Planck's constant times the frequency. That's true, but since the frequency of light can be anything, there's no law that says that a blob of energy has to be a certain definite amount, not like the blocks of Dennis. But there can be any amount of energy, at least at present understood. So we don't understand this energy as counting something at the moment, but just as a mathematical quantity, which is an abstract and rather peculiar circumstance. In quantum mechanics, it turns out that the conservation of energy is very closely related to another important property of the world, and that is the condition, that things do not depend on the absolute time. That if you set up an experiment at a given moment and try it out, and then do the same experiment at a later moment, it will behave in exactly the same way. Whether this is true or not, we don't know. But if we assume that this is true and add the principles of quantum mechanics, then we can deduce the principle of the conservation of energy. It's a rather subtle and an interesting thing, but it's not easy to explain at all. Now, the other two conservation laws then are all linked together. The conservation of momentum is associated in quantum mechanics with this proposition, that it doesn't make any difference where you do the experiment. If you move the apparatus over to one side, it'll do exactly the same thing. So the independence in space has to do with the conservation of momentum. Independence of time, so I always think of time as the fourth dimension, has to do with energy. And finally, if you turn your apparatus, it doesn't make any difference. And so the invariance of the world under rotation is related to the conservation of angular momentum. Besides that, there are three other conservation laws. I'm giving only the conservation laws which are known to be exact as far as we can tell today. There are three other conservation laws which are much simpler to understand because they are in the nature of counting blocks. The first is the conservation of charge. And that means merely that you count how many positive and negative electrical charges you have, and the number is never changed. You may get rid of a positive with a negative, but you don't create any net number of positives or negatives. Then there are two more that are analogous to that. One is called the conservation of baryons. There are a number of particles, strange particles. A neutron and a proton are two examples, which are called baryons. And in any reaction, whatever in nature so far, if you count how many baryons there are coming into a process, the number of baryons which come out is exactly the same. Finally, there's another thing, a conservation of leptons. There's another group of particles called leptons. I can count those, I can say what those are. Electron, mu meson, and neutrino. There's an anti-electron, which is a positron. That's -1 lepton. An antiparticle is -1. So counting the total number of leptons in a reaction, you'll find that the number in and the number out also never change. That at least is as far as we know today. Those are the 6 conservation laws then. 3 of them subtle, involving space in the form of, and 3 of them simple in the sense of counting something. Now, with regard to the conservation of energy, there are 1 or 2 remarks I would make. First, that energy, available energy, is another matter. There is a lot of jiggling around of the atoms of in the water of the sea. And so this, because the sea has a certain temperature. But it is impossible to get them herded into a definite motion without taking energy from somewhere else. That is, although from a fact energy is conserved, the available energy to human utility is not conserved so easily. And although there's energy in the sea, you can't get it out directly. The laws which govern how much energy is available are called the laws of thermodynamics and involve a concept of entropy, or irreversible thermodynamic processes. You see, the disorder which has been created, the jiggling which has been created in here now, is very hard to say with magic. Every atom shall turn around and the whole darn thing should go backwards until gradually this motion reverses and I get back my kinetic energy. It's very hard to do. In fact, impossible in practice. Although the energy is there, we can't get it out anymore. It has become, it's like if you mined iron and collected it into a pile and then let the rain run and it went into rust and it got dissolved in the whole earth all right, then in order to collect it all back together again takes a lot of effort. And it's that kind of a loss of energy. Although the energy is not lost physically, it's lost from a practical point of view. Finally, let me remark on the question, where can we get energy? Our supplies of energy today are all from the sun, the rain, coal, uranium, and hydrogen. The sun makes the rain, of course, and the coal also, so that all those are from the sun. Although energy is conserved, nature doesn't seem to be interested in it. She liberates an awful lot of energy from the sun, but only 1 part in 2 billion falls on the earth, so that nature has conservation of energy, but doesn't really care. She spends a lot of it in all directions. In the future, we expect to get energy. We have already gotten energy from uranium. We can also get energy from hydrogen, but it's now only an explosive and dangerous condition. If it can be controlled in thermonuclear reaction, then it turns out that the energy can be obtained from a quart of water a second is equal to all the electrical power generated in the United States. So with a faucet running 15 gallons of water a minute, you have the fuel to supply all the energy in the United States that's used today. Therefore, it's up to the physicists to figure out how to liberate us from the need for having energy. And it can be done in practice. Thank you. Dangerous game.